leverage one. This one is cook distance, okay? Influence on beta hat as a vector. Okay? I'm not talking about just individual vector, right? So, absolute value of di star large influence on fitted model. In general, I'm not saying on beta, on y hat, just in general influence on fitted model. So this one is influential effect of height observation on gate beta. On gate beta. And this one influence influential effect of height observation on y hat. So now these are in front of us. We can practice and see how residuals can help us to dig into the observations that we have and say more about our fitted model. Today. All right, so here is the data, table 8.5, page 413. That is about the past. We analyze this data regarding the constancy of variance and normality. Okay, so if we want to have all kind of residuals and information that I talked today, we should do two things when you are fitting the regression model, right? So here is the data. Okay, so we need to use a few columns for CT1 for X1, X1 for CT1, X2 for CT2, and just try to modify your data by producing new columns. So say X1, X2, do it in any way that is quicker for you. So these are the columns, right? What's that? CT for oh yeah, thank you. Sure. Cheers. Right. So the base CT now is CT4, right? Okay. So when you're making regression, after you selecting the dependent variable and explanatory variables, x1, x2, x3 plus traffic should come to the explanatory variables. Okay. So this one, okay. You can get all of those except this one when you save the prediction in the new data set. This one will not be saved and you need to do influential in the model. So you should do 2 jobs in order to get everything, right? So first of all, let's go to prediction, original sample, residuals, prediction limits, and then here, the agnostic statistics, this one, the agnostic statistics. That will give you everything, but will not give you the DF betas. For that one, modify task, means review code, and then go to the code after the model, put influential before the semicolon. So this is the model. Before that, influence. And run. So before the semicolon in the model, type influence, and then in prediction, pick mark the data, residuals, and diagnostic. So, okay, have a look at this table in this window. You will see that you have residuals. This is our student residuals or studentized deleted residuals, right? That is HI, half matrix, diagonal. And this is code ratio we didn't study. That is DF feeds. Okay? And then you see DF betas here. Right? But you don't see the others. For example, you don't see DI, right? Now, if you look at the output data here at the top, then you will see the Cook's distance here. Okay, this is H, this is Cook distance here, Cook. But you don't see DF betas. So some statistics are sharing between these two, but in order to have everything, you need to put both of them. Okay, so let's just start with the first one. Do we have a leverage point? Okay, we need to calculate some numbers, right? I have calculated these numbers. How many parameters we have in this model? We have beta 0, we have beta 1, and then we have 3 betas for the CP, right? So we have 5. So P is 5 and N is how much? You can see from the output is 24, right? So altogether you put them, you have these numbers. So for this one you have 0.4167. Then for 2 over root n you have 0.4082. And for 2 root n you have 0.9129. So these are the values that you can easily calculate for decision. So do you see any observation with HII bigger than 0.4? We can look into this column H, 0.4. Which observation do you see? Look carefully. Look carefully and write on a piece of paper the leverage points. Any idea? Any observation is leverage? Is that too hard? This is H. And do you see any observation with H bigger than 0.4 or something? The last one. Okay, write it. The 24th observation is a leverage one. You know, when you write it, then at the end you will have a summary that some observations are behaving badly. Then you can pick them, right? So this is the 24th observation, which is a leverage one. Now, for Cook's distance, do you see any DI greater than what? No. So, the idea is that there is no influential point, on the vector of data, right? There is no point that has, unusual effect on the estimation of all the parameters in general, right? As a vector. That is taken from Cook's distance. Okay. Now, DI star absolute value large, influential point on fitted model, and on the whole fitted model. So, that is the R student. The R student residual. This one. Oh, this is this. The R student. You have this one, R student. You see here? R student. So the R student one is this column. So what do you see? Do you have a large value, unusual value comparing to the others, of course? Yes. And one is negative 2.7, right? Negative 2.7. So how do you make decision on this? So I would say that observations number 3, number 5, and number 7 have almost large R student residuals, which may have influence on the feedback. Okay, I want to perform a significance test here. So this is what I guess, right, from the three values. But that EI star has approximately a t distribution. So we can perform a t test here with these observations, okay? So if I make a t distribution here, right? So that is the t curve. And for this one, how many degrees of freedom I have? So that is 24 minus t minus 1 is 17. df is 17. You can check this degrees of freedom in the class note that I showed you just now. And if you want here to have 0.025, then that point from the t distribution, you can get 2.11. So if absolute value of t star, absolute value of v I star is bigger than 2.11, then that point ith observation is significantly influential on what? On fitted model. So that is influential on the fitted model, okay, and that is significant. So what you selected, but just looking into the column of the R student, you just guess, right? But now you have a benchmark. Now, which one of those R student residuals is bigger than 2.11? The third one, okay? So you can conclude that the third observation is a significantly influential observation on the fitted model. Now we look into the DF betas. So this test is performed at significance level of 5%, right? Because the right tail is 0.025, the left is 0.025. So the significance level is 5%. You can test for 10%, okay? Change the value of 2.11. Maybe at 10% this is not influential, maybe. Right? So now you want to look into the DF betas, you cannot find it in here, right? But if you want to look into the DF feeds, you can find it here. So let me finish with the last one, and then I discuss about DF betas, right? So DF feeds, okay, anything absolute value bigger than 0.91. DF feeds. So we can find it here. The one before the last one, you see here. Okay, so which observation you see more than 0.91? The absolute value, of course. The third observation? The fifth observation? What else? No? No more. Okay, so we have the third and the fifth observation, influential observations on the fitted value, not on the fitted model, right? On the fitted value of y hat. Okay, now for df beta, we go to the result and look into this table. This part. That is coming from the influence option that we put in the model, right? So here is the intercept, right? We are not interested in this, right? We are interested in the effect of x on y. So we look into traffic, x1, x2, x3. This is CT1, CT2, CT3, and CT4 is the base. So now you can discuss any one of them separately. For example, you are thinking about the effect of traffic on sale, then you need to look into 0.4082. Do you have any observation here? More than that 0.41, approximately. The third observation, the fifth observation, right? And the 24th observation. You see, there is some trends coming out, right? The third observation, the fifth observation, and the 24th observation. So you can say these observations are influential. It is very important how to write it, right? It is influential observations on the effect of traffic on sale, right? On the effect of traffic on sale. So if you write your model like this, y E1 equal to beta 0 plus beta 1 traffic as traffic is 1. And then plus beta 2 x1 plus beta 3 x beta 1 beta 3 x2 plus beta 4 x3. So you are talking about this influential on beta 1 hat. And that is the effect of traffic on the sale, on the average sale. Right? So what do you think about CT1? For CT1. You can choose this one, you can choose that one, and what about this one? No. No, the last one is 0.4152. Oh, yes. So you can continue like that, okay? So I leave this one to you. So you can continue to find influential observations on the effect of CTs on the cell. So now what is the result? So we just selected some observations influential on parameters, on model, on vector of beta, right? So what can we say that? Yeah. So the observations that we are worried about that most of the others, maybe number 3 and 24, and maybe 5, right? So a good researcher think about the aim of the regression. What is the aim of regression? If the aim of regression is prediction, then that researcher should be very interested in TF fits, right? And the influence on the fitted model, right? These two. If you are interested in the effect of some X on the response, but your aim is not prediction, right? For example, you want to see if kind of medicine has effect on reducing the blood pressure. But you don't want to give people medicine and predict the pressure, right? So this is not the case. So in that case, you are interested in beta hat. So if you are interested in beta hat, you think about the Cook's distance, this one, and you think about the DF betas, right? Okay. Now next is that if I find observation number 3, as influential point, then what I do, I drop that one from the data, fit the model, right? And then compare the two models, the two results, right? With and without that observation to see, is beta is changing too much? R squared changing too much? Mean square error changing too much, right? If the answer is no, means that when I delete the third observation, I don't see any big change in beta, in prediction, in confidence intervals, in significance of p-values, R squared, so there is no point to drop it, right? So I keep it. I don't lose any information. But if the third observation is so that when I drop it, then I see, oh, the effect of X1 or traffic has changed a lot. Then I report both of them, right? And then look into the data that I put into the computer. Did I make a mistake in typing, recording the data? I try to find the source of the data, right? If that's reliable, no mistake, that is real data, then I report both of them, and I say that, okay, this is a rare observation, this is influential observation. With this one and without this one, we have this conclusion. And I don't make any judgment, right? I don't make anything, decide anything for people. I let people to be free to use with or without that observation. That is what we do. So if you have more than one, then you can drop one at a time, or drop all of them at once to see. So it all depends on your investigation. It all depends on how much time you have to work on the project, okay? And what is the purpose, prediction or estimation, right? Then you can play with the data, with the model, until you reach to a conclusion that sometimes, the third observation is so that it's very rare that in future you observe such observation. Then that makes sense to delete it, right? Because you want to use the model for future, right? So again, all depends on the purpose of the project. Okay, now let's have a look to the graphs. Some of these statistics that I did are now clear on graph, and that may be interesting for you. So this is residual versus predicted value for constancy of variance that we did before, right? This one is R student, and this is the line, you see? -2 and 2. That is for t distribution, approximately 1.96, approximately normal distribution, right? It is drawn by its SAS. So any point beyond these borders is called influential points. So this one is an influential point, right? Because this is less than 6, based on this. So with our student, what did we do? Which observation was influential? The I star greater than 211 was the same one, right? So if you go down, this is the sales versus predicted value. This is the one that does not depend on residual, but if the points are close to the line, y equal x, means model is good for prediction, right? Means the observed value and the predicted value are equal. Then y equal x, right? Okay. So this is another graph. This is the Cook's distance graph. So you see two borders, one in here, one there. Any point above this one is called influential. Now you have 2 points influential based on the Cook's distance greater than 1. The decision that we made there by comparing to 1 may be completely different from graph, because these lines are decided by stats based on some significance level of the task that we didn't consider, right? So if your document for discussion is graph, then you should stick with this graph and explain this one. Okay? Therefore, based on this one, we have two influential points. put distance, and here we are. This is the R student versus leverage. This is very nice one because it divided the space into 1, 2, 3, 4 parts. So if you know R student is small or large, then you can say that is influential. If it's more than a border, that is called leverage. So for this data, you have 1 point in here. Means that this value is leverage, right? It has, large X value. This one has unusual R student observation. So you see here, this mark is for outlier. This mark is for leverage. If you see any one in here, right, that would be leverage and outlier. That's very influential point, right? Or if you see some numbers in here, right, in this border, very influential and leverage. So this is another graph. You can have both of them in graph, okay? And residual versus quantile, that is for normality that we discussed before, right? And this one is residual fit plot, right? So this is the fitting, this is the residual. This graph is very hard for interpretation, but the thing that I can say about this graph is that the variability of the residual should not be more than variability of the fitted mean. So when you see these points, the variability of these points are very low. You see here, this is the range of variability. And that is much less than the variability of these points, right? From this point to that point. So this means there is nothing against the model based on comparison of the variability of residuals and the fitted mean. Perhaps I should mention this here, that if you have y equal to beta 0 plus beta 1x plus epsilon, right? This is the simple linear regression. So these are non-random variable, right? Therefore, whatever is the variability of epsilon should be variability of that one, right? So the variability of this should not be less than variability of y. That graph, check this one. If the variability of this one is much more than variability of y, then there is something wrong with the model. So this graph is for that purpose. All right? And see if there is any other graph. This is the box saying about 5 important numbers for the residuals: minimum, maximum, quartile, first quartile, third quartile, median. This is the mean. And if it's right skewed, left skewed, this is right skewed distribution, right? So against normality of residuals, right? And this block is very nice. If you want to report it in your project, I recommend to copy and paste this part for any report. That includes everything that you want, right? So the distance in here, that graph R student versus leveraging here. So everything are organized in one block for reporting if somebody wants to do. So from here is the DF feeds and DF betas. This is DF feed. So DF feed is greater than 2 over root P over N, the absolute value. So one line is approximately 2 root P over N, one line is negative. So you see that is 0.9, and this is close to 0.9. And this is negative 0.9. So all the points beyond these borders are called the influential on the y-hat. And we have 2. The third and the fifth observation, right? You remember that? That's the third, because this is 0, 1, 2, 3, up to 24. So this is the third and the fifth observation. And these are for DF betas. So intercept, traffic, x1, x2, x3. Again, you see the borders in here. And that is the 1, 2 divided by root n. which is 0.4, right? You see 0.408. Now these lines are 0.4 and negative 0.4, right? Approximately. So it means that if you have these graphs in front of you, you can interpret nicely the residuals, right? If you have those numbers, again, you can do that. But what we want to do is to learn about some kind of inferential test, formal test in case that you want to know that the VI star has a T distribution or Cook distance has a Fisher distribution. Okay, so I think that we know everything about graphs. And here is the R student versus traffic, R student versus 1. This is again something that you can think about the constancy of variance. For example, here you see the constancy of variance at two levels of x1 is violated, right? Because here is small, smaller variability comparing to this part, right? And this one is violated. Here is short variability comparing to this one, right? Same thing in here, right? And that one is violated. It's decreasing, increasing, decreasing, right? So now everything in this graph known to you. And I think you know that there are histogram of the residuals here. The yellow one is the kernel density. Kernel density is the density approximately put by the spline method on the histogram to approximate the histogram smoothly. So the yellow one is actually the actual distribution of residuals that we can do to the best to draw it, right? But the green one or blue one, or the green one here is the normal distribution you want to compare. If the difference between two graphs is too much, means violence against women. Do you think that anything else in this output I can explain for you about the graphical methods? This is the default. When you fit regression by default, everything will come up. And if you modify task, please, and then go to pause. So when you don't touch it, then you see all are shown. If you want to change the options, you can custom list, look at the custom list, okay? And then you can choose anything you want in here. Then you will not receive everything in the output. Okay, you will receive what you want. And here is an option to select it. All right. I think I need to explain one thing more about this part. Sometimes it's confusing to students that there are lots of columns in here, and I don't know about, for example, what is STDR, this one, for example. What does this stand for, right? So I want to write them on board for you, right? So that, when you want to read them, you know what are those columns for.